Hello everybody, and welcome to your video notes on Learning Target 6.1 at the MEETS level. 6.1 at the MEETS level says I can represent energy qualitatively, and remember that qualitatively means no math, with energy entering or leaving the system. So if you watch the basic level one, we just did LOL diagrams with no energy entering or leaving the system. The MEETS level is energy entering or leaving the system. So we're going to get started with what says number 2. This will be number 2 on your blue packet, but go ahead and try to do this just by writing this in your notebook to begin. So it says repeat problem 1. That's not important. For a frictionless system, so still no friction, but we're going to include the earth, the cart, the track, and not the spring. So go ahead and sketch this little picture in your notebook and sketch the LOL diagram, pause it, and then once you have that done, go ahead and hit play, and I'll show you the example. So to start off with, it's going to be important that we say that this is in our system. The dashed line represents our system. In the O of an LOL diagram, you're going to represent everything that's in our system. So we've got the cart, the earth, the track, and I'm not going to write spring in here this time. So because I don't have the spring in my system, I cannot say that we have elastic energy, because the spring is where the elastic energy is, and the cart's not being stretched or compressed, so there's no elastic energy. Forgot to do something else here, because I was going to talk about gravitational energy next. If you don't have a reference point, you can't talk about that. So we're going to say that the reference point is here, the lowest part of our picture. So the cart starts at the reference point, so no gravitational energy. Car's not moving, no kinetic energy. So we've got no energy in the system to begin with. In the end, however, we have the cart being some height above the ground or above our reference point. So we have to have gravitational energy. And it looks like here that there's some velocity that shows us that the cart's moving. So we have to have kinetic, but no elastic again, because there's no spring being stretched or compressed in the system. So we have to have energy in the system in the end. And if you'd watch the first part, we said that there is 2 bars in each. I'm just going to keep it the same for consistency. You could do 1 and 1, you could do 1 and 4, it doesn't matter. But this is what I did before, so that's why I'm doing it this way. If you would do an example like this in a different way, have 4 and 1 or whatever, all that matters is that the amount of bars work in the end or add up. Currently, my bars don't add up though, because on side A, I have 0 bars of energy. And in the end, I know that I need to have energy in the kinetic account and energy in the gravitational account. And I've got 2 in the kinetic and I've got 2 in gravitational. So that means that I have to have 4 bars going into the system. And the way you're going to show that is by doing something like this. I've got 4 bars here. I've got an arrow showing they're going into the system. Something else that you should do or get in the habit of is saying why and where the energy is coming from. So the why is you've got work on the system, and the work is coming from the spring. You have to be okay with being able to explain where this comes from. So the spring does work on the system, and we know that it's doing work because the spring is applying a force on the cart. If there's a force pushing the system some distance, we know that there's work. So the way that I would represent that in my qualitative equation is I do this. Work equals energy in the kinetic account plus energy in the gravitational account. And if we want our math to work out, we'd say, hey, look, 4 bars in the work account, 2 in the kinetic account, 2 in the gravitational account. Hey, how cool is that? It works out. So that's your first example. Example number 2 is number 9 on your blue packet, but again, I want you to try to do this one on your own, and maybe just write this in your notebook so that way you have something to study. So before I give you a moment to pause the video, I just want to explain this a little bit. Person's pushing a car with the parking brake on. With the parking brake on means that there's going to be friction. Up a hill, assume a system that includes the car, the road, the earth, but not the person. So that's an important thing to talk about. Our system is just the car, not the person. It says YA equals 0, so the position on the y-axis is 0 at the beginning, so your reference point is going to be like right here. VA, velocity at part A, is 0, so we're not moving here. And then over here it says y for part B, so we're some height above the reference point. The velocity equals 0, it's not moving. So go ahead, pause the video, see if you can do this one on your own. All right, welcome back. Great job, great try. Let's see if you got it right. So in the beginning, there's no energy in the kinetic account because it's not moving at position A. There's no energy in the gravitational account either because it's at the reference point. There's no elastic energy either because look at that, there's no spring. Okay, so this is another example where we have no energy in the beginning. Meets level questions will not always have no energy in the beginning. That just happens to be how the example works out this time. One thing I did not do, which I should have done first, I did this in the other video too. You have to do your system first. Oops. So your system, it says car, road, earth, but not the person. So car, road, earth. The road and earth aren't super important. The car is mostly the important part. So now we have to decide, well, what type of energy is there going to be at the end? And then what happens going into and out of the system? So let's start with position B. Do we have kinetic energy? We do not, because we said that the velocity is 0. Do we have gravitational energy? Yes, we do, because we're some height above the ground, but we have no elastic energy. So in the end, I'm going to say, you guessed it, 4 bars of energy. You could have done 3, it really doesn't matter, but I like the number 4. So, actually, oh, sorry for that noise if that was really loud. Turn down the volume on my computer. So, yeah, we'll do 4. Well, let's just see what happens if we do 4. So what's going to happen here is we have to have energy go into the system because the person is applying a force. So we're going to have energy go into the system, but we're also going to have energy that leaves the system because there's friction. So usually I like to have like 1 bar leave the system because of friction. I'm going to say friction causes E INT, which, if you don't remember, that's internal energy. So we're going to have at least 1 bar leave. So if we have 4 bars in the end and 1 bar leave, that means we're going to have 5 bars of energy go into the system. 1, 2, 3, 4, 5. I think that's 5. 1, 2, 3, 4, 5. Perfect. And then, things are getting a little cramped down here, so I'm just going to draw like an arrow, and we're going to say work from the person. The person is doing work on the system. So the person is going to add 5 bars of energy. 1 bar is going to leave because of the friction from the parking brake. And then this is how we'll have 4 bars in the end once it's all said and done. Here's what that qualitative equation looks like. We've got work minus the energy that ends up in the internal account that has to equal the energy in the gravitational account. And my math works out because I've got 5 going in minus the 1 from the internal account that's not losing the energy, but it's leaving the system. And then in the end, we get 4. Okay, so I chose 4 to begin with in the gravitational count. If I had done, say, 2 here, then if I have 1 leaving the system here, then I would have 3 bars of energy going in the system, 1 going out, and then I'm left with 2. So this is probably about as complex as it can get at the meets level, having some energy going in, some energy going out, and having some energy left over there in the end. Thanks for listening.